Hello everyone, my name is Tingyu Cheng. I'm a fourth-year PhD student at Georgia Tech. Today I'm excited to introduce our project Functional Destruction, which seeks to utilize sustainable materials physical transiency for electronics applications. This project was mainly conducted during my summer internship at the Central Future Technology Labs. I'm presenting this paper on behalf of all my talented colleagues from Accenture, especially my manager Andreea. Additionally, I would also like to thank my Georgia Tech advisors Gregory and HyunJoo for their invaluable support. Today, electronics are designed to be robust and durable with diverse functionalities and are also highly integrated. Besides the conventional PCB board that we have in almost all of today's IoT devices, we also print electronics in thin sheet form factor like paper for prototyping purpose, or weave the conductive yarn into our clothing to make interactive wearables, or even 3D print stretchable silicone-based electronics for personal health monitoring. We have all witnessed that more and more smart devices are produced, purchased by us, and become part of our everyday life. But what we really miss is where will these electronics go after you do not need them anymore? Do they just pile up around your room? Or do they end up in landfills? Have you ever thought of they perhaps are less easily recyclable than you have imagined? If we get a chance to open up a smart device, for example a home water leak sensor, you will always see a PCB board with a typical configuration like this. Flame retardant FR4, copper layers, numerous electronic components. As you see, the main challenge in recycling electronics is that they are often designed to be complex and robust for long-term use, making disassembly and separation of components difficult and time-consuming. And the current situation we are facing is that electronic devices may contain hazardous materials such as lead, mercury, which are contaminating our environment and even our health. Most of the products are designed with a fairly linear life cycle, starting with non-renewable resources and ending up as waste in landfills. And many of us continue to engage in unsustainable behaviors, such as buying new products when old ones break or do not have the latest features. So this linear model is not really sustainable, and as the resources become scarce and the waste accumulates, we must shift to a more circular one. We envision that when designing a new computational device, more circular thoughts should be involved. Can our device easily repaired, remanufactured? Can our device only last for a designated life and start to degrade without adding any environmental burden? So we propose functional destruction, where a device exists only within its prescribed transient destruction, and the destruction process is considered for enabling specific interaction. We have especially investigated how materials, fabrication tools, and different types of destruction can be combined to make devices with sustainability, transiency, and more importantly, interactivity at the core. For example, can we print a stretchable trace on a heat shrink film such that the shrinkage corresponds to a change in resistance? Can we use a hydrogel substrate such that water-induced expansion can be measured by a resonant frequency change? Or can we utilize the cracking of glass to create a signal relaying that damage has occurred? Under this design guidance and vision, in this work, we cover 3 practical approaches for building such devices, all of which are accessible to HCI researchers with off-the-shelf materials such as polyvinyl alcohol sheet, natural beeswax, and chocolate, which can be destructed under different stimuli such as water, heat, or digesting process. The first approach we introduce is a combination of PVA substrates with inkjet printed silver nanoparticle circuits. The fabrication process is very straightforward. One can simply print from a commodity inkjet printer. With this technique, we can simply make water-soluble devices like heater, interdigitated capacitor, or even an inductor. We have also studied how this destruction process can be more programmable. For example, one can increase the total PVA thickness to change the dissolving time of the entire device, or by using different water-soluble substrate materials to alternate the dissolving process. We also demonstrate by combining with hydrogel sheets we can create a water leakage sensor. As the hydrogel patch encounters with water, it swells and increases the circuit resistance till the entire PVA patch gets dissolved. The water in this case both activates and destroys the sensor. Besides water, heat is another very common and natural resource. Our second approach is based on natural beeswax to make sustainable electronics with two specific recipes. For the first one, we melted the beeswax pellets. Then we transfer printed silver nanoparticle trays to the melted beeswax. Doing so lets us create highly conductive patterns directly on the wax substrate. When exposing to high temperatures, the substrate melts, breaks the circuit, and functionally destroys it. Our second beeswax method is a graphite wax composite, which can be cast in a variety of shapes. Here we demonstrate using the composite to make an LED illuminating. We can also use the composite to make sensors, in this case for making capacitive touch sensor, or cast the composite into thin sheet and use it as a bending sensor. What we would like to highlight here is the reconfigurability of the composite. For example, the capacitive sensors we made can be remelted and casted into the bending sensors, where we do not lose or add any new materials through the process. We by the end also showcase how to combine these two recipes together to create a self-destroying device, where the resistive composite is utilized as a heater here. Our third approach is utilizing chocolate and edible gold leaf to create a variety of edible electronics. We first apply edible gold leaf to a substrate. We then laser etch the circuit pattern and transfer the etched gold leaf to sugar paper. Placing melted chocolate on the sugar paper transfers the circuit to the chocolate. We also demonstrate how these circuits might store information, letting a user look up information such as chocolate calories, flavors, or the consumption of the device. To further make our devices more sustainable, we also implemented a fully chipless C-shaped resonator, where the specific design and the dimension of the resonator can encode different information, and we utilize a nano VNA with two high-gain antennas for our implementation. And when the C-shaped pattern exists, we can detect a resonant frequency around 2.48 GHz, and when the devices are destroyed, we lose the signal. We so far have introduced three highly accessible approaches to fabricate a wide range of electronics that can go through different functional destruction process. We dedicated this section to further discuss the design and material selection rationale behind these three approaches, while also talking about the limitations we have observed and what could be the future directions to extend this work. In functional destruction, the substrate materials we used are mostly environmental friendly. For example, PVA can be considered as a biodegradable polymer produced from renewable bio-based monomers. Natural beeswax is heavily used as a biodegradable substrate materials and is reported to be completely degradable within 28 days. Chocolate is usually composed of a mixture of cacao, cocoa, and sugar ingredients, and is directly consumed for our use cases. For the electrode materials, the off-the-shelf graphite powder can be compostable. The silver nanoparticle is a water-based conductive ink and is environmental friendly. Edible gold leaf is also directly consumed with chocolate, and both the silver and gold electrodes used in this paper are of extremely small amount. Connecting copper wires, silver epoxy, and the surface mount LED in the beeswax demonstration are not green, and will cause negative environmental impacts without further post-process. One strategy is to replace these non-sustainable components with sustainable ones. For example, conventional LEDs or displays can be replaced with completely biodegradable electrochromic systems containing PEDOT-PSS electrochromic layers, gelatin-based electrolytes, gold electrodes, and cellular-based substrates. Battery is another inevitable component in all the electrical systems. For example, what is behind this water leakage sensor scene is that it is constantly powered. And meanwhile, batteries may contain materials like lithium, cobalt, and nickel. And if batteries are not properly disposed, they can release toxic chemicals and heavy metals into our living environment, which can contaminate soil and water and harm wildlife and human health. So instead of relying on batteries, what about if we can fully utilize the natural resources to harvest energy? For example, can we use thermoelectric nanogenerator to harvest energy from our body heat? or maybe use a solar panel to harvest energy from sunlight, and utilize the harvested energy to power our transient devices. We hope functional destruction can inspire considerations of how the end-of-device life can be a functional and also integral part of the interactive electronic systems. And I would like to end my talk here. Thanks for listening to our talk, and please check our paper for more details.